Hi, my name's Owen and I'm a PhD student at the University of Sheffield. Today, I'll be presenting our work on using developer-repaired flaky tests to assess automated flaky test detection techniques. A flaky test is a software test case that exhibits both passing and failing behaviour on exactly the same code. In other words, it gives an unreliable signal of the presence of a bug. Naturally, flaky tests cause a lot of frustration for developers and have a confounding effect on automated testing. Flaky tests are a common phenomenon, with around 60% of software developers experiencing them at least once a month. To combat flaky tests, the research community has introduced a whole range of automated techniques for detecting them. However, when evaluating these techniques, many studies follow a methodology that does not accurately assess their usefulness for developers. Ultimately, developers are the ones who decide which flaky tests to repair, and so it is vital to evaluate detection techniques from their perspective. One common such methodology is to calculate the recall of a technique against a baseline of flaky tests identified by automated rerunning, the most straightforward method for detecting flaky tests. This consists of repeatedly executing test cases to observe inconsistent outcomes indicative of flakiness. In this context, recall is the percentage of flaky tests in the baseline that are detected by the technique under evaluation. This methodology is limited because no prior work has established how well this particular baseline assesses a technique's usefulness for developers. Another common evaluation methodology is to simply present the number of detected flaky tests. However, this is limited because there is no baseline to assess recall against. Given these limitations, we performed a study to demonstrate the value of a developer-based methodology for evaluating automated detection techniques. To do so, we collected a baseline of developer-repaired flaky tests that is more suitable for assessing a technique's usefulness for developers. This is because developers allocated time to repair these specific flaky tests, implying they must have been of interest. Of course, this is not to say that flaky tests of a baseline derived from automated rerunning would not be of interest to developers, but rerunning alone cannot evidence this property by itself. Specifically, our study addresses two research questions. The first concerns the efficacy of the automated rerunning detection technique against our baseline of developer-repaired flaky tests. The second aims to take a deeper look at our baseline and identify what the causes and repair strategies were. To collect our baseline, we searched for commits among the top 1,000 Python repositories on GitHub with a query regarding flaky tests. We decided to target Python since many previous studies on flaky tests tend to focus overwhelmingly on Java. When we found a commit that matched our search, we checked commit messages, code diffs, and any other relevant information to determine if they repaired at least one flaky test. Once we were happy that this was the case, we identified and recorded every individual flaky test that was repaired in the commit. To promote the generalizability of our results by enabling the examination of more projects, we considered a maximum of 6 commits per project. By following this process, we ended up with a baseline of 75 commits that repaired flakiness from 31 projects. To answer our first research question regarding the recall of automated rerunning against our baseline, we developed our own framework to perform automated rerunning on Python test suites. Central to this framework, named Snowflakes, was a plugin to the PyTest testing framework. We selected PyTest due to its popularity and compatibility with other Python testing frameworks. We used Snowflakes to rerun only the developer-repaired flaky tests at the state of the parent for each of the 75 commits of our baseline. The parent of a commit is the commit immediately before. In this context, that's the state of the flaky test before the developer applied the fix. Beyond just rerunning tests, Snowflakes can also introduce 4 types of noise into the execution environment during reruns. This feature was inspired by previous studies that found that such noise can increase the probability of detecting certain types of flaky tests. The 4 types of noise we included were to randomly deprioritize threads, to randomly execute other test cases from the test suite and shuffle the test run order, to randomly limit the upload and download speed of the network, and to vary the minor version of the Python interpreter from versions 3.5 up to 3.9. We had Showflakes perform rerunning for each commit 1,000 times with no noise and 1,000 times with all 4 types of noise at the same time. In each case, it counts a commit as detected and a true positive if it can detect at least one of the flaky tests prepared in the commit, and a false negative if it cannot. Recall is then the number of true positives over the total number of commits. Because our baseline contains only positive examples, we cannot calculate true negatives, false positives, or precision. For the second research question, we manually classified the causes and repair strategies for each commit. When classifying causes, we used a previously established set of categories introduced by Luo et al. 3 authors categorized each commit individually and then discussed their findings to arrive at a consensus for the final cause categories. For the repairs, we did not have an initial set of categories, and so we followed a slightly different methodology to allow for one to emerge. Initially, one author inspected each commit and devised a minimal set of categories as a starting point. Then, 2 other authors used these categories to categorize each commit individually. As before, the authors then met to agree the final set of repair categories, their definitions, and the final repair category of each commit. This table shows the results of RQ1, highlighted for the top 9 repositories in terms of the number of flakiness repairing commits we sampled. The first numerical column, commits, indicates the total number of commits from that project in our baseline. The next column, no noise, shows how many commits were detected by rerunning without noise. The final column shows how many were detected with noise. As the results show, rerunning with noise attained a better recall than without noise, but at just 40% of the 75 commits is still low. This table shows the results of RQ2. The labels down the rows show the cause categories. The labels across the columns show the repair categories. Each cell shows how many commits were in that cause and repair category. Totals for the causes and repairs are in the final column and row respectively. The most common cause category was randomness, which developers addressed in 15% of commits. This category involves test cases that use, or cover code that uses, random number generators and is flaky due to either not setting seeds or not anticipating the full range of the generator's potential outputs. Randomness was followed by async wait and time, both at 12% each. The async wait category concerns flaky tests that make asynchronous calls but that do not properly wait for them to finish. The time category is for test cases that are flaky due to their reliance on date and/or time. The most common repair category in our baseline was widen assertion, which developers applied in 25% of commits. This involves adjusting an assertion statement to make it accept a broader range of values and states. Add mock and add / adjust wait were tied for second place at 15% each. Respectively, these involve mocking the behavior of a class or function and adding or adjusting a time delay in the test case code. For the flaky tests that were repaired by developers in the study commits, we can say that they allocated time to do so, and so they must have been of interest. The results for RQ1 showed that automated rerunning with noise achieved a recall of only 40% against these commits. This is not to say that the flaky tests that could be detected by rerunning, but that are not part of our baseline, would not be of interest to developers, yet we cannot say anything about those flaky tests since we do not know if developers would assign time to repair them. Still, we demonstrated that the intersection between the flaky tests detected by rerunning and the flaky tests that we can say were of interest to developers is small. This implies that, for developers, the usefulness of rerunning is limited. We found that rerunning with noise performed significantly better than without. This finding supports the results of previous studies. Therefore, if developers do wish to use rerunning to detect flaky tests, we strongly recommend doing so with noise. It is common in previous studies to evaluate detection techniques using the flaky tests identified by automated rerunning as a baseline. We found that rerunning did not perform well against our baseline of developer-repaired flaky tests. This implies that a baseline provided by rerunning would be unsuitable for assessing developer usefulness. given that this property is what our baseline aims to assess. Thank you for listening.